Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to study the test error of linear regression models in order to understand when we can expect it to be small or large. This is important because the test error reflects to what extent the models generalize to new data that is not in the training set. Let's get to it. We're going to talk about the test error of linear regression models. Let's remind ourselves that in the regression problem, we want to estimate a quantity of interest, which is called the response, from multiple observed quantities that we call features. In an example that we have been using in several other videos, and we will use also in this one, the response is the temperature in Versailles, Kentucky, and we want to estimate it from temperatures at 133 other locations. So we have 133 features. In our video on linear minimum mean squared error estimation, we showed that if we represent the response as a random variable y and the features as a random vector x with d entries, where each entry corresponds to a feature, then the optimal linear estimator in terms of mean squared error is of this form. What we do is we center the features subtracting their mean, then we apply linear coefficients that correspond to the inverse of the covariance matrix of the features times the cross covariance between the features and the response, and finally we add back the mean of the response. Now a key question is, how good is this estimate? How well does this estimate actually approximate the response? In order to explore this, let's take a look at this model of the response, where the response does actually depend linearly on the features, but there is some added noise that gets added to it, which captures everything that does not depend on the features. So we assume that this noise is independent from the features and has a certain variance. For simplicity, we're going to assume that everything is centered, so we don't have to worry about these additive constants where we center the features and then we add back the mean of the response. Now think about what the mean square error of our linear estimator of the response given the features should be. Here, if you realize, there is a part of the features, a component that is, a part of the response that is indeed linearly related to the features, but there's another part which is not. And we cannot expect to be able to estimate that part. So ideally, the mean squared error would be exclusively this orange part on the right, which is the noise that is not related to the features. Because everything is centered, the mean squared of that component is just its variance, which we assume is equal to sigma squared. So ideally, we should observe an error of sigma squared when we try to approximate the response using our model. Great. So if we assume that the response is of this form, and we apply the linear minimum mean squared error estimator, then in the video on coefficient error, we showed that you actually recover the true coefficients. And that means that when you look at the error that you incur when you approximate the response using your estimate, which is the linear coefficients, because again, we don't have any additive constants because we assume everything is centered, times the features, then what happens is that the estimated linear coefficients correspond to the true ones, and y we are assuming is equal to this linear component plus the noise. So what happens is that these two guys cancel out and we're left with the noise, which indeed has variance sigma squared. So great, everything seems to work out perfectly. Is this the end of the story? Can we, call it a day and say that linear regression, the linear minimum MSE estimator is just going to produce the error that we expect it to produce? No, because in practice, when we fit linear regression models, we don't have access to the full distributions of the response and the features. We don't have access to their full joint distribution. Instead, we have to compute these models from data. Instead of computing this linear minimum mean squared error estimator, what we actually do is we compute the ordinary least squares estimator from a finite data set that has n examples, where each example consists of a vector of d feature values and the corresponding response. And from these n examples, we compute the linear estimator, which we showed in the video on the ordinary least squares estimator. On the video on ordinary least squares, we showed that this estimator actually is optimal in the sense that it fits this training data as well as possible with a linear model in terms of residual sum of squares, in terms of the sum of squared errors. And it just turns out that you can obtain it very easily by replacing the cross-covariance between the features and the response by the sample cross-covariance observed in the data. Same for the covariance of the covariance matrix of the features. You just replace it by the sample covariance matrix of the features in the data, and you take the inverse. And then same for the means. Okay, the mean of the features is replaced by the sample mean, and the mean of the response is replaced by the sample mean of the response in the training set. Great. So now let's take a look at how this OLS estimator performs for some real data. As I said at the beginning, we're going to be interested in a problem where we want to estimate the temperature in Versailles, Kentucky. That's our response, from 133 features that correspond to temperatures at other locations in the United States. If we fit the model with a lot of data, so here the number of training data is very large, these are the linear coefficients that we observe. So here I'm plotting, on the one hand, the location of Versailles, so the location of our response, where the temperature corresponding to a response is measured. And I'm plotting also the linear coefficients in the OLS model for a large number of training data. And the way I'm plotting them is as circular markers, where the radius is proportional to the amplitude of the coefficient. And what we see is that we have three large coefficients that correspond to locations that are pretty close to Versailles, which makes a lot of sense. And the other coefficients are all very small. This happens when we have a lot of training data. Now let's take a look at what happens when we have different amounts of training data. So here I'm plotting the linear coefficients for different amounts of training data. That's the horizontal axis. When we have a lot of data, what we observe is that there's three coefficients that dominate, and those three coefficients, which are represented by these three black lines, correspond to the ones that are geographically close to the response. But when we don't have as much data, so here we observe that there's wild fluctuations in the coefficients, which sometimes drown out the relevant, the truly significant, I don't know if significant is the word, like that's maybe not the best word, but the truly geographically meaningful coefficient. We studied all of this in the video on coefficient error, and we showed that it's associated with overfitting. In the video on training error, we showed that we had like a good theoretical explanation of what is going on here, where the coefficients are going crazy. We see overfitting in the training error, and also what we see here, where we have a lot of data, we don't overfit the training data. In this video, we're going to try to understand a little bit better why the training error has this shape. That's going to be the goal of this video, where when we don't have a lot of data, the test error explodes upwards, and when we have a lot of training data, the test error is the same as the training error. That's what we're going to try to understand in this video, and for that we cannot use our linear response model where the features are a random variable, here we have to explicitly account for the fact that we have a finite number of training data. In order to do that, what we're going to do is we're going to change our linear response model. We're going to keep the additive noise, and we're going to still assume that the response has a linear component that depends on the features. But now, instead of modeling the features as a random variable, we're going to explicitly assume that they correspond to n feature vectors that are fixed. Okay, so now our response, just to be clear, our response is going to have, if you don't mind, I'm going to ignore the train, this sub, sub index, I don't know how to even call it, to just not clutter notation, okay? But this is y train that I'm writing down here. So y train is going to have n entries. Why are they random? So remember that in all of these videos, when we have a squiggly line on top of a variable, that means that it's a random variable. They're random because we're adding random noise to each of them. So here again, I'm not going to write train under each z, but hopefully you will forgive me for that. So for each entry of the response, we have the inner product. Maybe I'll erase this. For each entry of the response, we have the inner product of the corresponding vector of features times the true coefficients, and then we add an entry of the noise vector, and that gives us the corresponding response, okay? And then this happens for every entry of the response. The whole point of this is to no longer model the features as a random variable, so that we can account for the fact that we have a finite number of training data, and we can try to understand the test error in this regime, which is closer to what happens in reality. We're going to assume that these noise entries are all IID, and their variance is sigma squared, and they are independent from the features. For simplicity, everything is centered to have zero mean, so that we don't have to worry about additive constants in the linear model. So now what we're interested in is looking at coefficients that are obtained from the training data, which we assume has this form that I just explained. We're going to use this training data to estimate the linear coefficients in our linear regression model. And now we want to study how well those coefficients allow us to fit test data that has not been seen by the model. This test data is going to correspond to vector of the features that we model as a random vector, and a corresponding random variable that models the test response. We're going to assume that, and then we're going to evaluate the test error. We're going to see how well the linear model that depends on the coefficients estimated from the training data once we take an inner product with the test features, how well that approximates the test response. Our assumption is that the test response is connected to the test features in the same way that the training data. Okay, because otherwise what are we doing here? We're assuming that there is some common linear relationship in the training data and in the test data, because otherwise why would we expect the linear model to generalize? And this test response is corrupted by noise that is independent from everything else. What is important also here is that we're assuming that this guy, the test features, are independent from the training features. I mean, of course they are, because these are just deterministic vectors here, but we are assuming that they're not in the training set. That's what I'm trying to say. As I said, the noise that corrupts the test data is assumed to be independent from everything else. It has this variance sigma squared, just like the noise in the training set. Okay, so under these assumptions, let's try to characterize the test data of the linear regression model. So we already know from our video on coefficient error that the OLS coefficients using this model are going to be centered at the true coefficients. They have zero bias. It's an unbiased estimator. And we know that their covariance matrix has this form where basically the variance in every direction becomes smaller as we these are the variance of the coefficients, of the OLS coefficients. It becomes smaller in every direction when we increase the number of training data. It's proportional to the variance of the noise, which makes a lot of sense. And then it's also proportional to the inverse of the covariance matrix of the features. As a result, in directions where the features have low variance, the variance of the coefficients explodes, producing a lot of coefficient error. We already studied that in our video on coefficient error. Now we're going to see how this is reflected in the test error. We want to understand how the coefficient error propagates to the test error, propagates to how well we can approximate the response in test data. Okay, so this is the test error. We know that this guy can be decomposed into its mean, which is equal to the true coefficients and whatever is left. So this, by definition, is just the OLS coefficients minus their mean, which happens to be equal to, this guy is just equal to beta true, as we proved in our video on a coefficient error, and I just mentioned. And what we observe is that under this decomposition, this guy and this guy cancel out, okay? Because we're assuming again that Y test is connected to the features through these same true coefficients as the training data. So in that case, we're left with a test error that corresponds to the test noise, which we're not going to be able to approximate, so we can forget about it, and a term that is very important, which is the inner product between the test features and the centered OLS coefficients. Now here we have a little bit of bad news and a little bit of good news. What is the bad news? Well, the bad news is that, as I said, in directions where the features have low variance, the OLS coefficients can have high variance. When I say that the features have low variance in a certain direction, this is because there is feature collinearity and limited data often. We talked about this in the video on coefficient error. The good news is that if you realize, because there's this inner product between the centered features and the test error, and the test features, so there's this inner product between the OLS coefficients and the test features, in these directions where the OLS coefficients have high variance, we know that the features have low variance, so they canceled out. So this guy is going to have high variance precisely in the direction where this guy has low variance, as long as the covariance structure of the features in the test data is the same as the covariance structure of the features in the training data. So the coefficient error does not necessarily propagate to test error. Now we're going to prove this mathematically, but I wanted to just start with some intuition about what is going on. And again, what is going on here is that there's a cancellation between the variance of the OLS coefficients and the variance of the test features, because the OLS coefficients have high variance in the directions where the training features have low variance. So if the test features also have low variance in that direction, then this will mitigate the effect of the coefficient error on the test error. in order to prove this mathematically, what we're going to do is we're going to look at the mean squared error of the test set, where here basically what we're doing is we're taking the test response, subtracting the linear model, just taking the square and seeing what that is equal to on average. That gives us, that is the mean squared error on the test, on our test data. If you realize this, the test, we already said that the test noise is independent of everything else. So in particular, it's independent from all of this, and everything is centered to have zero mean, if you remember, so that just to simplify our derivations. So this means that this mean squared error is equal to the variance of the error. And now we can decompose that variance into the sum of the variance of each of these components, because the components are independent and hence uncorrelated. So we have the variance of the noise, which we know is equal to sigma squared. And now we have this term that we need to analyze, which is where this cancellation that I just talked about happens. Now here, in general, the way we go about this kind of expressions, at least previously in previous videos, is we just want to take stuff out, right? But remember that you can only take out stuff from this expectation operator if it's deterministic. You cannot take random variables out of the expectation operator. However, here we observe that all of these variables are actually random. So what do? We have to do some slightly more sophisticated mathematics. Notice that this guy and this guy are independent from these guys. Why? Because the OLS coefficients are computed from the training features and the training response, and all of that is assumed to be independent from the test features. They might have the same distribution, they might have the same covariance structure, but the actual samples observed during training are independent from what we will observe in test. That's the whole point of held out data. So we might think of decoupling these two terms and then applying the fact that the expectation of the product of independent random variables is equal to the product of the expectations. That's not so easy to do because this guy is on the left and this guy is on the right. So what are we going to do about it? What we're going to do about it is we're going to use the trace operator. So the trace operator is the sum of, let me do a little drawing here. So imagine that you have a matrix. Wow, amazing. That was supposed to be a square matrix. Another amazing picture. Okay, this is a little bit better. This is a squared matrix. The trace operator is the sum of its diagonal, of the diagonal entries. Notice that in this particular case, this is a single number. Okay, this is the square of the inner product of the test features times the centered OLS coefficients that I've chosen to write like that. It's a single number, so of course it's equal to its own trace, because a single number is a 1-by-1 matrix. The sum of its diagonal is itself. Why are we doing all of this business? Well, it turns out that the trace, oops, sorry, I still have this straight line tool activated. So the trace of two matrices A and B, such that A times B happens to be a square matrix. Let me draw A and B. A and B. Again, as you can see, I'm not the best at drawing stuff. Wow, that's supposed to be a rectangle. I'm just going to do it, give it another shot. Okay, that looks like a rectangle. Okay, so this product of A and B, which will produce a small matrix like this, okay, if we compute its trace, that is going to be exactly equal, and this you have to look at a book on linear algebra or prove yourself. It's not so difficult to prove. this exactly equal to the trace of B times A. And notice that B times A produces a very, here I'm going to be maybe lazy and I'm just going to copy this. Copy, paste, yes, and copy, just because I'm so bad at drawing. This produces a very different matrix. Okay, because now when I consider this, the product of B times A, the resulting matrix is going to actually have very different dimensions. It's still going to be square, but it's going to look like that. However, its trace, the sum of its diagonal, is exactly equal to the trace of A and B. Why is this important? Why does this help us out? This helps us out because now, if I'm taking the trace of this whole expression, I can actually take this guy and move it all the way over there where it's with its friend that is very related to it. It's exactly the same thing but transpose, and separate it from these guys that are independent, so that then later on we can separate them into the product of their corresponding means. Okay, I hope that made a little bit of sense. These are just mathematical details that are not super important, but just so that you see where our result comes from. Okay, so now we have moved this guy over there because the trace of A times B is equal to, just to be clear, in our here we're going to treat this as A and this as B. Now we're going to move B to the other side. Going to be trace of BA instead of trace of AB. This is exactly what we do. Now we can't just say that this is equal to the mean of the product because we have this trace operator here. But if you realize, the trace of a matrix is a linear operation, meaning that if I sum two matrices, the trace of their sum is going to be equal to the sum of their traces. You can just check that out. Or if I scale a matrix, then its trace immediately gets scaled. Because of that, we can apply linearity of expectation and perform the trace after we take the mean. And now we're in very good shape because, as I explained before, the test features are independent from the test response and the test features. So in particular, they're also independent from the OLS coefficients computed. Did I say from the test? I think I said it well, but I'm just going to say it again just in case. The test features are independent from the training features and from the training response. And the OLS coefficients are estimated from the training features and the training response. Hence, that red component and this purple component are independent, and we can apply a result that we talked about when we talked about averaging, where the mean of a product is equal to the product of the means, as long as the different random variables are all independent, and here they are. So that finally we have this expression here, which corresponds to the covariance matrix of the test data, and this expression here, which corresponds to the covariance matrix of the OLS coefficients. Okay, and we have the trace of that. Now we have to ask ourselves, what is the covariance matrix of the test coefficients? Perhaps a reasonable assumption is that the covariance structure of the test features is the same as in the training data, because again, we're assuming that at least the distribution of the data is preserved from the training to the test set, because otherwise we can't really expect our model to generalize. If that is the case, and this is important, and that covariance matrix of the training data is reflected in the sample covariance matrix that we actually observe. This might not be the case if we don't have enough training data, and this will become very important later on, but let's assume it for now. If that is the case, then we can just plug in the sample covariance matrix of the training features into there and multiply it times the covariance matrix of the OLS coefficients, which we know are proportional to the inverse of the sample covariance matrix of the training features. So these guys are going to cancel out. We're going to end up here, well, they don't cancel out, they're equal to the identity matrix because we have D features, and these are sample covariance matrix of the D features. That identity matrix has a diagonal that has D entries, so that in the end, its trace is just going to be 1 plus 1 plus 1 D times. We have an expression for this component of the test error that is proportional to the test noise, to the number of features, and is inversely proportional to the number of training data. If we put it together with the other component that came from the test noise, actually, by the way, here this is not, I said the variance of the test noise, that's not true. It's the variance of the training. It's the variance of the training noise that has propagated to the OLS coefficients and then to the test error. Just to be clear, it's just that we're assuming that it's the same as the test noise, and this is the test noise. So when we put everything together, we get an expression for the test error under the assumption that the covariance matrix of the test features is the same as the sample covariance matrix of the training data. And under this assumption, if we have enough data, if n is large with respect to the number of features, the number of training data is large with respect to the number of features, then this is going to go to 0, and we get our ideal result where the MSE, the test MSE on held out data, is equal to sigma squared. So the linear regression model is generalizing well to the test set. Now, what happens when n is approximately equal to d? You might be tempted to say, well, then this is more or less 1, so the test error is equal to 2 sigma squared. But, and this is crucial, we have assumed that the covariance matrix of the test features is the same as the sample covariance matrix of observed in the training data. But if the training data are not enough, if they're quite small with respect to, if their number of training data is small with respect to the number of features, then that sample covariance matrix is not necessarily going to reflect the true covariance structure of the features. So this is not going to be true. Not because the training data are not sampled are not generated according to the same distribution as the test features, but rather because we don't have enough data to approximate this covariance structure from using the sample covariance matrix. Okay, if that happens, then our assumption does not hold anymore, and the explosion in the coefficient error, remember that the coefficient can have high variance in directions where this sample covariance matrix has a small, well, basically the observed training data has small variance. That is not going to, there's not going to be cancellation because that covariance structure of the features in the training data does not correspond to the true covariance structure that is observed in the test data. Okay, so that cancellation does not happen anymore, and we cannot expect the formula to hold. We probably will observe much more test error. Let's go back to our real data. Here, as in our video on training error, we're going to assume that this level of error is sigma. Okay, where the training error is equal to the test error, we assume that there is something that is not linearly related to the response that we can just not approximate when we have a lot of training data. So we're going to take that value and replace it by the sigma in our formula. And then the rest we can do, right? Like once we have this guy in our formula, we can just plug in the number of features and the number of training data and plot our theoretical estimate of the test error. And our theoretical estimate of the test error is really, really good until this point. It really shows how the test error is going down with the number of training data, but it doesn't account for this explosion of test error that happens here, and that is precisely the regime in which the sample covariance matrix of the training data is not going to reflect the true covariance matrix of the features, because we don't have enough training data for the sample covariance matrix to approximate the true covariance matrix. So there is not this cancellation between the coefficient error and the test features, the variance in the coefficient error and the variance in the test features, and boom, the test error explodes. The linear regression completely overfits and does not generalize well to the held out test data. And it's exactly what we see on our real data experiments. So what have we learned? We have learned that the test error depends on the number of training data n. When n is large, we can expect strong generalization to held out test data from linear regression models, and that's what we observe in our real data experiments. When n is close to the number of training data is close to the number of features, we observe overfitting. We don't generalize well to held out data, and interestingly, this is not only because of coefficient error, it's also because of the inaccurate estimation of feature covariance, because we don't have enough training data for the sample covariance matrix of the training data to truly reflect the covariance matrix, the covariance structure of the features, because if that were the case, then it would cancel out the coefficient error. And that's all I have. Thank you very much.